Hi, everyone. Welcome to my session on object detection with transformers. Really excited to be speaking at the Data and AI Summit this year. My name is Liam Lee, and I'm a machine learning engineer at Determined AI, where we're building the leading deep learning platform for state-of-the-art training and hyperparameter search. So today, I'll be talking to you about how to train these new object detection models with Determined and then deploy them with MLflow. So this talk is split into three sections. First, we'll go over object detection just so we all understand what the problem is. Then I'll go over the detection with transformers architecture and also some follow-up work to that called Deformable DETR. And both of these models are some recent approaches that have been introduced in the research community that I find to be very exciting. And then finally, we'll talk about how to train and deploy these models with Determined and MLflow. So what is object detection? I think we've all probably seen something like the video I'm showing here, where basically for each frame of the video, we have a model that's generating predictions about where the location and also class of different objects in that particular frame are. So that is the goal of object detection, is to be able to identify the location and classes of objects in an image. And object detection is a really core task in computer vision because it's a building block for many downstream tasks like pose estimation, event detection, video understanding, and so on. So today we're going to be focusing on object detection, and one data set that's used a lot in the research community is called the COCO dataset for object detection. And here we're looking at one of the images from the COCO dataset, and each image has a bunch of different associated annotations with them, corresponding to the image. And each annotation consists of a class label, a segmentation mask, which is shown here on the right image, where we have a list of XY coordinates creating a polygon mask of the object. And from the segmentation mask, we can derive bounding boxes like the green box shown here by just taking the minimum and maximum of the XY values over all the coordinates. So for object detection, we're not going to be using the segmentation mask. We're only going to be focusing on predicting the bounding box coordinates. The segmentation mask is used for other tasks like semantic segmentation that are kind of related to object detection, but we won't be talking about that here. So given the data, the prediction problem then is basically to take an image and then output a bunch of bounding boxes as well as associated classes for that image. So most of the approaches nowadays use deep learning models to be able to generate the predictions. And you can see here, we have a combination of large and small boxes that somewhat correspond to the actual objects in the image. So to evaluate the performance of a model, we have to be able to take the predictions that the model generates and then match them to the ground truth labels. And then finally just evaluate so the quality of the bounding boxes as well as the correctness of the classes. So to do that, there are kind of two metrics and two concepts we need to be aware of. So first is intersection over union. And here you can see in the first image, we're showing the intersection between the ground truth green bounding box and the predicted black box. And then on the right is the union of those two boxes. So as you can imagine, the higher the ratio of intersection over union, the better our bounding box. And with this notion of IOU, we can start setting thresholds to determine which predicted boxes we should actually consider as having an object in them. So you can imagine we set a higher IOU threshold, then we'll get fewer predicted bounding boxes. Whereas if we set a lower IOU threshold, we'll get more predicted bounding boxes, but some of them might contain noise or just bad predictions. So the next step is calculating the actual metric that we're interested in. And for object detection, the metric that people usually use is called mean average precision. And to understand this metric, we first need to understand some metrics, some submetrics, let's say. So the first is precision, and precision basically tells us how good our model is at predicting positive predictions. So what portion of the positive predictions are actually correct? So how precise is the model when it's making positive predictions? Another metric is recall. So here, recall is trying to capture what portion of the true positives we are actually capturing with the model. So the higher the recall, the more of the actual true positives we are able to detect. And as you can imagine, if we set a higher IOU threshold, that will correspond to higher precision because we're requiring that the bounding boxes be higher quality, but that also consequently usually means lower recall. So there's this trade-off between precision and recall, and to capture the performance of our model for multiple trade-offs between precision and recall, we simply average the precision over different IOU thresholds. So that's how we can calculate mean average precision, and this is the main metric through which models are evaluated. Okay, so let's jump into the DebtR and Deformable DebtR models. So the first question that you might have is, why should we care about DebtR? And the main sort of innovation of DebtR is it replaces a lot of the custom components in existing object detection networks with transformers and simplifies these pipelines significantly. So we've seen transformers have revolutionized NLP, but not so much computer vision. So it's a natural question to ask whether transformers are also applicable to computer vision. And as I said, existing methods like the one shown below here called faster RCNN, which is a very popular approach to object detection, have a lot of hand-designed components that are difficult to implement and introduce a lot of complexity. So if we just look at a few of these, we are training a separate network called the region proposal network that's used to generate areas of the image that we should focus on. And then there are a bunch of components after that to kind of filter, deduplicate those predictions to get to a reasonable set at the end. With DebtR, all of these sort of expert design components are just replaced with a standard transformer encoder decoder architecture. So we don't have to worry about these more complicated components up top. We can just use basically the standard implementation of transformers that you can get access to in, say, PiTorch, and use that as a layer in our object detection models. You can see the DebtR architecture is much simpler. So what does it actually look like? Let's dive in a little bit more. So we'll kind of walk through the architecture step by step to get kind of more detailed understanding of what's happening with the DebtR architecture. So first, there's a backbone, and this part is shared across almost all object detection approaches. Some commonly used backbone are the ResNet architectures that are trained on ImageNet. So we use a backbone architecture that has image features, and we unroll them into a sequence of inputs because that's kind of the data that's expected by the transformer. So the transformer operates on sequences and not images. So we flatten that sort of output from the backbone into a vector. And then next, we add positional encodings to kind of add positional information to that vector. Without the positional encoding, we don't know how the unrolled pixels relate to each other. So we need to have some information to pass to the transformer that says, okay, this pixel is here and relative to that pixel. So that's why the position encoding is used. And then that sort of joint vector is passed to the transformer encoder. And if you're not familiar with transformers, you can think of the encoder portion as basically learning how to attend across sequences for each position of the sequence. So if we look at the outputs here, we have an image of cows, and for each of the pixels, we're showing what the attention mask looks like. So if you look at the red point on the brown cow, you can see that the attention mask corresponding to that pixel is learning to focus on the body of the cow. And we have kind of similar masks for other pixels in this image. So the encoder is just learning how which pixels are important for a particular pixel when making the prediction, the downstream prediction. The output of the encoder is then passed to the decoder. So if you remember from the faster RCNN architecture, there were 200,000 something regions that were generated for consideration of having a potential object. So the DebtR architecture doesn't generate 200,000. What it does instead is it says, okay, I'm going to fix the number of object queries that I think are in the image. So for most cases, 200 is more than sufficient, which is what they use in the paper. So they fix the number of potential bounding boxes. And then the decoder basically takes the output of the encoder. And for each of those possible objects, it tries to learn how the encoded output should influence the class prediction of that object query, right? So if we look at the decoder output for each of the bounding boxes, which you can think of as a single object query, we're learning to focus on certain regions of the image. So if you see the highlighted parts of the elephant, those are kind of the outputs from the encoder that the attention weights has decided to be important for the prediction of the elephant, right? So the decoder is basically learning how to attend to the outputs of the encoder for its class predictions. And then finally, the decoded output get passed to prediction heads that generate the bounding boxes as well as the class predictions. And the class predictions can be no object if there doesn't seem to be anything meaningful in a particular object query. So how do we train the network? So if you recall, we get basically predicted bounding boxes and classes from the network. So to train it, we have to match those predictions to ground truth. And that is done in DebtR with basically, it's called a bipartite matching algorithm called the Hungarian algorithm. And what we're trying to do with this algorithm is match the predictions to the ground truth. And it's a one-to-one matching. So that's why it's called bipartite matching. So for every single ground truth label, we're going to match a single predicted bounding box and class to that. And finding this matching is done by minimizing the loss that you see here. And the loss has two components. The first component basically is trying to maximize the class probability. So we want to match predictions that have very high probability assigned to the true class label. And the second component is kind of capturing how good the bounding box is. So we want boxes that match up very well with the true bounding box. So if we minimize this loss, we get a matching, and that is the matching that we use to form this loss here, which has kind of the same two components, and it's differentiable, so we can just use backprop to update the weights and train our network. So how well does DebtR perform? So here I'm comparing the performance of DebtR to faster RCNN, which is a pretty standard object detection network. And you can see that DebtR is able to match the performance of faster RCNN with respect to the mean average precision, but there's still certainly some drawbacks of DebtR. So in particular, you can see DebtR converges slowly. We require 500 epochs to reach the same performance as faster RCNN. Additionally, it has poor performance on small objects, and this is attributable to using a single layer from the CNN backbone. So if you take a single layer, we just get one resolution of features, and we'll talk about how to improve upon that with follow-up work next. So follow-up work that kind of addresses both of these issues was done by Zhu et al. In their paper that introduced deformable DETR. And the main contributions are in this paper are a deformable attention module that uses sparse attention instead of kind of dense full-on attention. And it also extends DebtR to use multiscale features. And we'll talk about what each of those contributions are in detail soon. And in combination, both of those features are able to help deformable DebtR converge much faster and do so with fewer samples. So let's see what the improvements are. So if you look at kind of why DebtR converges so slowly, the problem is basically attributable to the fact that we're unrolling CNN features into a very long sequence. And transformers are known to work poorly on long sequences of text, and a similar thing holds here for images. So what happens is when you have a long sequence, the attention mass is spread thinly across all the items in that sequence. So it takes a long time for us to learn something meaningful to attend to. And the long sequence also means it's computationally intensive due to the quadratic dependency. So why is it quadratic? In standard attention, for a fixed point in our sequence, so say we're looking at an image and we have a query vector that we want to attend to, we need to look at all the other pixels in this image for a particular query. And when you do this for all the queries in an image, you wind up with a total of height by width dot product. So that's why it's quadratic dependence. And for long sequences, this is very expensive. And the solution that the authors of the Deformable DebtR paper came up with is called Deformable Attention. And their insight is that instead of attending to every single pixel in the image, we're going to learn just a few values that we should attend to for a particular query. So instead of looking at HW pixels, we're going to look at K, with K being much smaller than H by W. And the location of these K values are learned. And then we wind up with a much smaller number of total dot products for attention. So we're going to learn where to focus on instead of trying to attend to everything. So that helps with kind of the convergence rate. The other question is, how can we improve performance on smaller objects? And if we look at kind of other works in object detection, there are a lot of methods that make use of what are called multiscale features. So instead of just taking the last layer of the CNN backbone network, we're going to take multiple layers, and each layer has a different resolution. So you have the top layer that's lower resolution, and then as you go deeper, you get higher resolution features that you can use to make your predictions. And multiscale features are an important component of many object detection approaches. You can see some of them below. And what the authors of the Deformable DebtR paper do is they are able to take advantage of multiscale features by generalizing the deformable attention mechanism that we looked at before to apply to multiple resolutions, right? So now instead of applying attention to a single layer of the backbone, we're going to do so for multiple layers. And that basically allows us to look at features that may be relevant in different resolutions and then use that to boost performance on hopefully smaller images. So how well does deformable DebtR perform? And if we look at the convergence curves or the learning curves for deformable DebtR versus normal DebtR, we see that deformable DebtR does converge much faster in every single step of the learning curve. And if we go back to the table before, we see that deformable DebtR is able to exceed the performance of faster RCNN and DebtR with just 50 epochs of training. So we do converge a lot faster, like I said, because the attention weights now is not spread out across 800 things. It's spread out just across, say, 20 different points. And if you look at the performance on small objects, deformable DebtR does do much better on smaller objects and matches the performance of faster RCNN. So the multiscale features are definitely also helping here. And And if we look at kind of state of the art in object detection, which I would say efficient DET is definitely one of the leading methods out there. Deformable DETR with a better backbone achieves very similar performance to efficient DET. So we are able to scale up deformable DETR to larger models and match the performance of state of the art with a much simpler pipeline for object detection. Okay, so let's finally start talking about how you can train these really cool models that are coming out from the research world. So we're going to be looking at how to do training efficiently with Determined. And Determined is basically a training framework for deep learning. And we focus exclusively on training to make the experience great for the user. And basically you can think of Determined as fitting in the middle here, where you can interface with other solutions before and after model training to kind of help you with data preparation and pre-processing in the beginning. And then after you train your model with Determined, you can interface with deployment solutions shown on the right. So I think the core features of Determined that make it super useful for model developers are kind of shown in the middle here. So we offer state-of-the-art distributed training. You can also use state-of-the-art hyperparameter search algorithms with kind of a leading early stopping-based approach that I developed as a PhD student. You can also just use the platform to do experiment tracking and cluster management. So it's really easy for you to just focus on model training and not have to think very much about the DevOps aspect of training models at all. So we'll go a little bit into how to do training with Determined in the demo. And then we will talk about how you can deploy your models using MLflow serving. So let's dive right into the demo. There's a link here. You can follow the notebook as I go along. The notebook won't be connected to a Determined cluster, so you won't be able to submit experiments, but I think it'll still give you a good idea of how you can use Determined for training. And if you're interested in training these models yourself, we have implementations of DebtR and Deformable DETR available in a repo for you. So let's see how you can train DebtR models efficiently with Determined and then deploy them with MLflow. So here we're looking at a notebook that's running on a Determined cluster with a GPU connected. And first, I'm just going to import all the necessary modules and then have some helper functions so that we can use it to visualize the COCO dataset that we described in the first part of the presentation. So this dataset here, we're reading it from a Google Cloud Storage bucket. And let's just take a look at one of the images so that we can see whether things look reasonable. So here we have a man holding a tray of hot dogs with the ground truth annotations shown on top of the image. So this is kind of what we're trying to predict with our object detection models. So let's see how you can train the DebtR model in Determined. So the first thing you have to do is define a DebtR trial that implements the PiTorch trial interface for the DebtR model. And if you're familiar with PiTorch Lightning, our PiTorch trial is basically the same as what's expected for a Lightning module. It requires certain functions to be defined for your model so that we can go and train your model for you. And certain functions are expected by PiTorch trial, and these functions basically tell us how to create the data loader as well as how to perform the training and evaluation steps for your model. So in the initialization function, we're building the DebtR model using the same code that's provided in the GitHub repo open source by Facebook AI Research for DebtR. So that's what the function that we're calling here. So that's the build model function. And then we're creating the optimizer and LR scheduler as well, and making sure Determined is aware of the model, the optimizer, as well as the LR scheduler by passing those objects to the Determined context. Other functions that Determined requires are the build training data loader as well as the build validation data loader functions. And these are pretty standard. functions for building the data loader. But determine does go and shard the data loaders for you automatically if you're performing distributed training. And then last are the train batch and evaluate batch functions, and these are very similar to the functions that you would write outside of determine that specifies how to create the loss function and then take a backward pass on it before making a step on your optimizer. So once the trial is defined, determined, the next step is specifying an experiment config to go along with that trial definition. And the experiment config specifies things like hyperparameters and also how long you want to train the trial for and how often you want to evaluate for. You can also see you can specify the GPU resources that you want to use for the trial. And then enabling distributed training and scaling up to more GPUs is as simple as changing this slots per trial experiment field. You don't have to modify your model code whatsoever in order to scale up to distributed training. So that's kind of one of the big benefits of doing things in determine. Once the experiment config is defined, you can then submit it to the determine cluster to run by running this command line, the CLI command in a terminal. So let's go ahead and do that so we can see the experiment in the determine web UI. So we'll first go to the experiment directory that has the model and experiment config defined, and then we can just simply execute this command to send experiment 434 to the cluster. So this is the determined web UI, and it's very useful for monitoring the state of your experiments as well as monitoring the state of your cluster. So if we go back to, let's find the experiment that I just created, which is 434. We can see that it's active right now, and the master is basically provisioning resources to satisfy this the GPU requirements for this trial that we just submitted. So we'll come back to this experiment a little later. In the meantime, let's talk about how you can also very easily run HP search and determine. It's basically as simple as modifying the experiment config to define a search space via ranges for different hyperparameters instead of constant values. So once you define the search space, then you can configure the hyperparameter search algorithm you want to use. We support a state-of-the-art hyperparameter tuning method called adaptive OSHA that uses early stopping to significantly speed up hyperparameter search. And similar to the experiment before, you can just submit it again to the cluster by running a CLI command. So let's go back to the experiment that we submitted before and see how things are looking. Here, experiment 434, we now see the trial. There's a trial that's active. And here we can see the validation metrics that have been computed during training for this trial. You can zoom in on the trial and see other metrics that are being generated by this experiment here. So we have a bunch of different validation metrics as well as training metrics. If you want, you can view these metrics in greater granularity in Tensorboard. We store those metrics every batch instead of larger intervals as shown here. And we're also saving checkpoints automatically during training for you. So if a validation metric exceeds the previous best, we'll take a checkpoint. So you have access to that checkpoint later. This supports automatic fault tolerance. So if your instance fails while an experiment is running, determine will just go back and relaunch that experiment for you if you specified that for your experiment. So once your model's trained, determines taking checkpoints for you automatically in the backend for automatic fault tolerance, and you can register those checkpoints with our model registry for easy access by running some commands here. I've done that already for one of the DebtR checkpoints that I trained previously, so we can easily load it for use with MLflow. So now the checkpoint is loaded. I'm going to make sure MLflow is installed. And then to deploy a model, all we have to do is kind of massage the determine checkpoint into the format that's expected by MLflow. So that's what's done in this wrap DebtR module to sort of get the structure to what is expected by MLflow. And we can save this model with MLflow along with the environment dependencies as well as files required to execute the model by running this command. And once the model is saved, we can serve it with the simple command line, executing a simple command line command, CLI command for MLflow as well. Go back to the work directory where the MLflow model is stored, and we can run this command to get a REST API endpoint up where the model is sitting waiting for predictions. So once the serving endpoint is up, we can then just submit submit images to the endpoint for predictions with this function. And let's see what the output looks like for the first image in the validation data set. It's taking a while because the GPU is not quite warmed up yet, but here we can see the predictions from DebtR. For the most part, it looks pretty good. The only one that looks a little bit off is the refrigerator, but it is doing something pretty reasonable for the other objects in this scene. So this kind of concludes the demo, and if you're interested in running any of this yourself, there's a link in the presentation to where you can find the code. So if you're interested, definitely go and check it out. Yeah, so thank you for your attention. And if you want to learn more about how to use Determine AI or MLflow, you can go and visit the associated websites. And again, your feedback is really important to the organizers, so please don't forget to rate and review the sessions. Thank you.